All right, so put the homework right next after this. So they got a little dark up here. Um, and just to remind you about all this stuff. So just also double checking myself. Yeah, so I'll post the homework here as well. Okay. All right. So do, 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 do. All right, so I only gave you 8 more, which should be sufficient for our purposes of getting some practice with this. And so again, the vertical asymptotes are always the denominator equals 0. And here degree of the numerator 1, degree denominator is going to wind up being 2. So automatically y equals 0 horizontal asymptote. Y and x-intercepts are both the same. So we have one dot. We have our vertical asymptotes. And since there were no other x-intercepts, I kind of figured this would be the graph, since if x is greater than 1, these are all positive, right? And so I did the same thing here. But you could always use a test point if you're not sure, right? So I did that on the either side of 1, so I used 1.1 and 0.9. And so 1.1, notice you put that in, you get 3 positives. That's why you see that there. And over here, when you put 0.9 in, then the x minus 1 becomes negative. So that just confirmed the direction on the left and right side. And then I did the same thing over here at negative 2.1, just for the sake of it, you know. So when you put negative 2.1 here, these all become negative, and so that confirms that that's the correct side to go down on the asymptote. Now 14, you had to do the polynomial division to get the second asymptote, because degree 4 is bigger than degree 2. Okay, and so here's the polynomial division. So we wind up with a nonlinear asymptote. So again, the quotient is always the asymptote, because this remainder fraction is going to go to 0 as x gets big. So over time, this graph looks more like x squared plus 4, which is a parabola. And so that's what you see me doing here with the sketch of the asymptote. And then the denominator equals 0 is always the vertical asymptote. And then x and y intercepts, when you solve the x-intercept, it's always numerator equal to 0. And so you wind up taking the 4th root, so you're going to get plus and minus. Okay, so then we got some intercepts we can plot. Now this is an even function, so that means it should be symmetrical. And that's helpful. So it should be symmetrical on either side of the y-axis. And since there's only there's only 2 x-intercepts, then on the far right and far left branch, this is going to have to go up. Otherwise, we cross the x-axis again. So again, you can use some of the symmetry and knowing how many x-intercepts you have to help you with this. Same thing here. Now this time, the degree of the denominator was bigger, so it's always going to be a horizontal y equals 0 asymptote. Degree of the denominator equals 0, you get your vertical asymptotes. And then numerator equals 0, you get your x-intercepts. So then we can plot. This is also an even function. So that means we know we're going to have symmetry on either side of the y-axis. All right. And so this right here told me that we had to go down, and that no other x-intercepts means the left and right branch have to be above, since there's no other x-intercepts. Okay. Right, and then 32 had a little wrinkle because it had this exponent of 2 on the x minus 4 denominator factor. So that gives some credence to even multiplicity. I'll point out what that means in a moment. If we get to degree, we're going to wind up with x cubed and x cubed on top and bottoms. Those are the leading terms. And so the coefficients 1 over 1 is the horizontal asymptote. Okay, again, that's why that's good to know. Okay, so vertical asymptote, denominator equals 0, horizontal asymptote y equal 1. finding the y-intercept, replace the x with 0, and so you're going to wind up with not applicable because division by 0. And the numerator equals 0 produces the 3 x-intercepts. So you've got a whole lot of x-intercepts. All right, so when you sketch the asymptotes, well, the one on the left branch, this would make the most sense because we only have one x-intercept over here and approaching the y-axis. Whereas the branch on the right, same thing, and then once we know the x and y-intercepts, we know that middle branch. But if you notice where the exponent of 2 occurred was on the x minus 4. So that means on either side of the 4, there's no change. And so that's why both of these graphs are going straight up. Now, even if you didn't know that, you can still use a test point. What happens on either side of the 4? And so on either side of the 4, 4.1, 3.9, these are all still positive. Normally, the 3.9 minus 4 would become negative, but because it's squared, that stays positive. So again, test points can be helpful if you don't catch some of the little subtleties about the even multiplicity. And I didn't do that on the left branch, but you could have did that too. On the left branch, you could have used, what am I looking for? Yeah, you could have used negative 0.1. So just a little to the left of 0. Negative 0.1 you could put all in here, and you would be able to see that if you needed that help. And I just went ahead and thought, well, wait, what's in the middle of this? That's another way you can tell. So if you get a negative in the middle of this, that means it has to be open up, right? And so I just went ahead and found that. I put the 2 in for x, calculated. I found that little location. It's another thing you can do. Now, these do get complicated, but there's only one even exponent. So that means there's only going to be one multiplicity issue on either side of the 4. So there's not going to be any touching and bouncing on x-intercepts because we didn't have even exponents at the top. And that's how these things can get complicated. But you didn't really have that issue. I'm just pointing that out. Okay, now here, you wind up with a hole because after you factor, the x minus 3 whole asymptote is eliminated. So that means this looks like x plus 4 over x plus 2. So notice y equals 1 because the 1x, 1x. So 1 over 1. And vertical asymptote is now only at x plus 2 equals 0. So I just sketched that. We had the y-intercept and an x-intercept. And that was helpful because now we got the branches. Okay, and then wherever the graph occurred on the right branch when x was 3, I put a little circle since before simplification, that would have been an undefined issue because it would have caused division by 0, but after simplification, it's not relevant. So we just use a hole to indicate that singularity in the original unsimplified function. Okay, and then you had these last 3. Now these last 3 were already in remainder fraction form. So these are the results after the polynomial division. And so you can just look at that first term to get the asymptote, and all 3 of them were linear, which was good because those tend to be easier. And in this case, they were pretty much all the same, you know, which was, I thought, interesting. But solving the x-intercept might have been a little tricky because you would have to rearrange the original equation. So I got a common denominator, and then I just put the numerator equal to 0. Okay, so for 40, that doesn't exist. And the same thing happened, getting a common denominator, and then you wind up the numerator equals 0, again, square root of a negative. And that happened also with 44. I got a common denominator and then put the numerator equal to 0, again, a square root of a negative. So that means if it can't cross the x-axis, it has to be in these locations. Those are the only locations for the left and right branch, because if it wasn't in that location, it would have to come down and cross the x-axis. So knowing that there's no x-intercept helps you find the left and right branches. in relation to the two asymptotes, which is helpful.